download our Revise It Right revision app for hundreds of videos, quizzes, exam questions, tutor support and so much more. This video is about nuclear equations. Now when a nucleus decays, the mass number, atomic number and charge is conserved. When alpha beta decay happens, the nucleus transmutes or turns into another element. And it can be represented by a nuclear equation, where you have the element going through radioactive decay on this side, and then the new element plus the type of decay on this side. And what we mean that the mass number and atomic number is conserved, it means that the mass number and the atomic number on the left is the same as the mass number and atomic number on the right. Now let me just put this into context for you so you may gain a bit of an understanding, and let's go through a worked example. So uranium-238 goes through alpha decay. So we're going to do a worked example of uranium-238 going through alpha decay. So first things first, what we need to do is we need to write uranium down on our working document. Okay, so we've got uranium, which has a chemical symbol of U, and here it tells us our mass number of uranium is 238. So it's an isotope of uranium with a mass number of 238. It's important to note when you look on the periodic table, uranium might be showing a different mass number, and that's because this is an isotope. Write down the one you've been given. If you haven't been given a mass number, then you would assume that the one on the periodic table is what you write. And then you need to find the atomic number of uranium by going to the periodic table, finding uranium and looking for the atomic number. The atomic number of uranium is 92, so we can write that here. Now uranium is going through radioactive decay, it's actually going through alpha decay. So what that means is it's going to spit out an alpha particle. And we know that an alpha particle, as we're going to write here, has a mass number of 4 and an atomic number of 2, as it contains 2 protons and 2 neutrons. So we know that uranium going through alpha decay is going to spit out an alpha particle here, which has a mass number of 4 and atomic number of 2. But we also need to find out what new element is going to be formed when uranium goes through alpha decay. And it's very, very simple to do. Remember, the mass number and atomic number need to be the same on both sides. So if the mass number is 238 on this side, it needs to be 238 on this side. And we already have 4, so to find what we need now, all we have to do is 238 minus 4, and that gives us 234. So the mass number of our new element is going to be 234. We apply that same logic to our atomic number. It's 92 on this side, and we've already got 2 on this side. So to find out what new atomic number, we do 92, take away 2, which equals 90. Now to find what new element that forms, we have to go to our periodic table, look for the element with the atomic number of 90 and write it in. And that is thorium. And we write it in there. Now be aware, again, when you look on the periodic table, thorium might have a different mass number. Then that is because it is an isotope. Always look for the atomic number, as the atomic number, remember, never changes. Elements always have the same amount of protons, so always look for that atomic number there. And as you can see, that gets us thorium. And that is our complete radioactive equation, our nuclear equation. And we can double check our work by checking that the mass and the atomic number is the same on both sides. So here we have 238, and here we have 234, add 4, which equals 238. So that is the same on both sides. And our atomic number, here we have 92, and here we have 90 plus 2, which equals 92. Therefore, our atomic number is the same on both sides. Let's go through another example of alpha decay. So this time we've got radon-222 going through alpha decay. So the first thing we need to do is find radon on the periodic table and write it in. So we got Rn for radon, given us our mass of 222. Remember, the one on the periodic table might be different. Write down the one it tells you in the question. And the atomic number of radon on the periodic table is 86. Now we know this is going through alpha decay, so we can write in our alpha, which has a mass of 4 and an atomic number of 2. Now that we need to find our new element that this is going to form. So we do 2, 2, 2, take away 4, which obviously gives us 218. So our new element has a mass of 218. And we need to find our atomic number. 86 minus 2 is 84. So then we need to look on our periodic table for the atomic number of 84. Okay, and it's polonium. So it's P and O. So there we have our nuclear equation for alpha decay of radon-222. We can double check. 222 mass on this side, 218 add 4, which equals 222 on this side, so that is balanced. 86 atomic number here, 84 add 2 here is equal to 86. So there we go. That is our nuclear equation for radon-222 going through alpha decay. Remember to download our Revise It Right revision app, watch over 700 videos, answer 4,000 plus quiz questions, over 1,000 flashcards, 1,000 exam questions, worksheets, forums, and get help from qualified teachers and so much more. The link is in the description. So now let's go through an examples of beta decay, and here we've got thorium 234 going through beta decay. The process at the start is the same, so we need to write our thorium, and it's given us a mass of 234. We look on the periodic table and it has a proton number of 90. Now this time this is going through beta decay, which is an electron, and we know that this has a mass of 0 and an atomic number of -1. Okay, now for every beta particle emitted, a neutron in the nucleus has turned into a proton. So what you see is the atomic number is going to go up. So the same rules apply here. To find our new mass, we do 234, take away 0 as nothing has been lost in terms of mass. So our new mass will stay at 234. Now this is where it may get slightly more confusing, but it doesn't have to be. It's still quite easy. It's 90 plus -1. Okay, so 90 minus -1. This is where it may get slightly more confusing, but it doesn't have to be. So we've got 90 minus -1 gives us 91. So the atomic number has actually gone up. Because remember, for every beta particle emitted, a neutron is turned into a proton, which means the proton number is going to go up by 1. Then we need to look on our periodic table and find our atom, our element that has a proton number of 91, and it's palladium, so we write in there Pa. Okay, and then we need to check that they're the same on each side. So we've got our mass is 234 on this side, and 234 add 0 is 234 on this side, and our atomic number is 90 on this side, and then 91 plus -1 equals 90 on this side. So it is the same, and that is how we do our nuclear equation for beta decay. So we'll go through one more just to make sure that you understood that, and this time we'll go through iodine 131. So again, we need to find it on the periodic table. Iodine, symbol I, mass number 131 in the equation, and when we look, it has a proton number, atomic number of 53. We know that's going through beta decay, so it's going to emit an electron with a mass of 0 and a proton number of -1. A neutron is going to turn into a proton, so we know the mass number is going to go up. 131, take away 0 to find the mass, is 131. And 53 minus -1 is 54. Then what we do is we've got to go onto our periodic table, find the element that has a proton number of 54, and that is xenon. And there we have our equation for beta decay. Mass this side is 131 and this side 131, so that's correct. This side it's 53, this side it's 54, add -1, which is 53 as well, so it is balanced. Now gamma rays don't change the charge or the mass, and that is because if we go back to our gamma ray, they have 0 mass and 0 atomic number. So a nuclear equation for gamma radiation would look like this. Let's take uranium-238 as an example. So we've got uranium-238, and that has an atomic number of 92. This going through our gamma radiation would obviously produce our gamma wave, which has a mass of 0 and an atomic number of 0. And therefore, the mass number wouldn't change, so that would stay at 238. And the atomic number wouldn't change, so that would change at 92. And therefore, the element wouldn't change, because it has the same atomic number. So it would still be uranium. So that is what a gamma nuclear equation looks like. Not much change. What I'd now like you to have a go at is answering these 3 questions here to really practice your nuclear equations. So pause the video now. Okay then, let's go through the answers. So for number 1, you should have had lead-210 undergoing beta decay and therefore producing bismuth, which has a mass of 210 and an atomic number of 83. Then you have polonium-214 going through alpha decay. So it's produced lead-210 with an atomic number of 82 plus the helium nuclei or the alpha particle 42. So that should have been your answer for that. And for question 3, bismuth-214 going through beta decay, therefore producing polonium with a mass of 214 and an atomic number of 84. You can now practice these more with our quiz, where we've got plenty more practice, and our exam questions as well. And if there's anything you didn't understand, then please get in contact with one of our tutors who will happily help.